here, we are going to finish up our unit on stoichiometry by talking about a topic called limiting reactants. And depending on who your teacher is and what year it is, don't know the page number, but find the page that says topic 4, limiting reactants, and we're ready to go. So before we can talk about chemistry limiting reactants, we're going to use an analogy, an example. So we are going to look at this picture over here and think about what is called a place setting or a place. So at a standard dinner table spot, we would find the following items. We would find one dinner plate, one fork, one knife, one spoon, and one napkin. So that's a standard plate, or sorry, a standard place setting. So if you open up your cabinets at home and you find the following items, 7 spoons, 8 forks, 8 knives, 3 plates, and 10 napkins, how many place settings can you make? So think about that for a moment, pause if you need to, and figure out how many place settings you can make. So the answer is that we can make 3 place settings. 3 total settings can be made because then you run out of plates. And once you run out of plates, there are no more place settings, okay? You cannot make a complete place setting without a plate. So that's it. So we could phrase this and say that plates limit the number of place settings you make. They are what's called the limiting factor because they determine how many places you can set at the table. So in chemistry, we would call that a limiting reactant because it limits how much stuff we can make. So here are the big ideas. When chemicals react, one chemical will run out first, okay? You can also think of this like cooking. If you are cooking as many cupcakes as you can possibly make, eventually you're going to run out of one ingredient. So you're going to run out of something. The one that runs out, so the chemical that runs out, is called the limiting reactant. And that will determine how much product can be made. So the plates were the limiting reactant, and they determined how many place settings we could create. The final big idea, the others are called the excess reactant. So in our setting the table example, what substances, what parts of a place setting were in excess? It means we had too many. Spoons were in excess. We had too many spoons. Forks and knives and napkins, we had too many of those. So those were called the excess reactants, and the plates in blue were called the limiting reactants. All right, so getting our vocabulary down, the limiting reactant is the first reactant. It is a chemical with a chemical formula, is the first reactant used up in a reaction. So it gets used up, and so we could even say that the final mass left over of that substance is at 0 grams. None is left over. And that is what's going to determine how much product can be made because it limits the reaction. The other reactant we call the excess reactant. Extra is usually added of this particular chemical to make sure that the other reactant is completely used up. There's going to be some leftovers, and leftovers are considered waste. And so the excess reactant is usually going to be the chemical that is cheaper and also easier to recycle or reuse. So the limiting reactant is the one that runs out. The excess reactant is the one that we have too much of, and there is some left over. So what are the steps to determine the limiting reactant? Well, first, just like all stoichiometry, we write a balanced equation. Then for each reactant, because in a limiting reactant problem, it's going to have at least 2 reactants, so maybe like A and B forming C. For each reactant, calculate the amount of one of the products formed. So that is going to be 2 stoichiometry calculations or problems. So yes, it's going to take a while to set that up, but this is a crucial piece of information to find out what the limiting reactant is. So what I would do is convert from A to C and figure out how much C could be produced based on A. I will also convert from B to C and figure out how much C can be produced based on the amount of B that I have present. Step 3, we're going to focus on the smaller answer. The smaller answer will indicate the limiting reactant. It's the reactant that calculation started with. And the answer will tell you the maximum amount of product that can be made. So the bigger answer, you just completely exit out. Like everything about it is a lie. And the smaller answer is the one that is telling you the truth. So we're going to jump right into a practice problem and see how this will work. So we've got number 1 here. And let's start by reading. So it says 10 grams of aluminum reacts with 35 grams of chlorine gas to produce aluminum chloride. And there's our balanced equation for it. You know, looks pretty standard, pretty simple synthesis reaction. Which reactant is limiting, which is in excess, and how much product is produced? So these problems are easily recognizable because of the information that they give you. First off, they're going to give you 2 numbers. We have 10 grams of aluminum and 35 grams of chlorine. Both of those chemicals are reactants. So I'm even going to write them above the chemical in the balanced chemical equation. For aluminum, I specifically have 10 grams. For chlorine, I have 35 grams. So when you have a question like this, where, like I highlight here in blue, you have the amounts of 2 reactants, this is a limiting reactant problem. And you're going to go through this process that we're about to walk through, okay? The question is going to ask us how much aluminum chloride is produced. So I'm going to put question mark grams. All right, so the way that we solve this problem is we convert aluminum to aluminum chloride. We also convert chlorine to aluminum chloride, and then we will compare our answers. So get ready, stick with me. This will take a little while, but we can do it. So I'm going to set up my first stoichiometry calculation starting with aluminum. So I have 10 grams of aluminum, and I'm going to go all the way to what I'm highlighting over here in pink, all the way to grams of aluminum chloride. So here we go. Grams of aluminum. My first step in the molar roadmap, if I'm at grams, is to go to moles of the same chemical, moles of aluminum. Then that comes down diagonal, moles of aluminum. And I convert to my other chemical that I'm eventually solving for, moles, which is AlCl3. And finally, I bring that down diagonal, moles of AlCl3, and I'm going to grams of AlCl3. All right, I'm going to move this a little bit so I have room to write my answer when it's ready. Okay. So let's focus in on our numbers to plug in. When I have mole to mole, I use the coefficients. Well, aluminum chloride and aluminum have coefficients of 2. So I'm going to put 2's right here where my red dot is bouncing. So 2 and 2. These other ones are moles to grams, and that's when I use 1 mole equals the molar mass in grams. So I'm going to put a 1 in front of the moles. And the molar mass of aluminum is the one that I'll start with. That is 26.98. And then up here, I've got aluminum chloride. I'm going to grab a calculator and add 1 aluminum and 3 chlorines. So 26.98 plus 3 times 35.45. The molar mass of aluminum chloride is 133.33. Okay, so we're ready to calculate this. I'm going to multiply across the top, so 10 times 2 times 133.33 divided by 26.98 and divided by 2. I get 49.4. And that is grams of aluminum chloride. Now, when we're doing a limiting reactant problem, you are going to do 2 of these calculations. So we just did, if I zoom in here and look at my plan, we just did 1 calculation from aluminum over to aluminum chloride. Now we're going to do the same thing, but starting with the other chemical, chlorine to aluminum chloride. So this time we're going to start with the 35 grams of chlorine. So 35 grams of Cl2 chlorine Bring down diagonal grams of chlorine, go to moles of chlorine. Bring down diagonal moles of Cl2, and we're going to moles of AlCl3. And then bring down diagonal moles of AlCl3 and go to grams of AlCl3. All right, so first up, mole to mole, I like to start with that one. Aluminum chloride has a coefficient of 2. Chlorine, however, has a coefficient of 3. So a coefficient of 3 on the bottom and 2 on the top. My next two conversions are moles to grams. I'm going to use 1 mole equals the molar mass grams. So 1 mole. And then the molar mass grams. Oh, look at this, y'all. I already know the molar mass of aluminum chloride is 133.3. So that's going to go right here. 133.33. And then the other one down here is chlorine, but it needs to be doubled because it's diatomic. So 35.45 times 2 is 70.9. All right. To calculate this one, I'm going to multiply across the top. So follow along. 35.0 times 2 times 133.33 divided by 70.9 and divided by 3. I get 43.9 grams of AlCl3. Okay, that's the hard part, y'all. Doing 2 stoichiometry problems, it takes a while, you know? We're just gonna be honest with ourselves, it takes a while. But interpreting it is not so bad. So if we go back up here, we're gonna focus in on step 3. The smaller answer indicates what the limiting reactant was and the amount of product that can be made. So what I like to do is look at my 2 answers here. I've got 49.4 grams of aluminum chloride or 43.9. The smaller one is correct. The bigger one, I just like to exit out. I just feel really good doing that. Goodbye. That one's wrong. It's a bunch of lies. It's not going to happen. So instead, the smaller answer is the truth. So, number 1, which reactant is limiting? Was it aluminum or chlorine? Well, it was the one that gave us the smaller answer. It's chlorine. So I like to write limiting reactant equals chlorine, Cl2. What's the excess reactant? That's the one that we had extra of. So it's not the chlorine, it must be the aluminum. So the excess reactant equals aluminum. And the final question here is how much product is produced? Well, good news, y'all, we already solved that. That's the amount of aluminum chloride product produced. So I'm just going to label it product produced and kind of put a little circle around that. All right, y'all. So everything that I put a box or a big circle around here is part of the answer. So that is how stoichiometry works with limiting reactants. And just to kind of sum up and again remind you what we saw here, if you have a chemical reaction problem that gives you a mass of both reactants, so they told us how much aluminum and how much chlorine we had, you are going to use this limiting reactant approach. Let's continue with problem 2. So problem 2, again, gives us a balanced equation, and it tells us 15 grams of potassium reacts with 15 grams of iodine. Now, notice that these are the same mass. That actually is not going to be helpful because they're different chemicals, they have different molar masses, so you cannot compare the grams. So we're going to calculate which reactant is limiting and how much product is made. So I like to start again by writing down underneath each chemical or above it how much I have. I have 15 grams of potassium and I have 15 grams of iodine. And my question is how many grams of Ki are going to be produced? I'm going to do 2 calculations to Ki and pick the smaller answer. All right, so let's set up my first one. So I'm going to start with 15.0 grams of potassium. I'm going to bring down grams of potassium and go to moles of potassium. I'm going to bring down moles of potassium and I'm going to go to moles. Remember, where are we going? We're going to Ki. So I'm going to go to moles of Ki. And finally, I'm going to go from moles of Ki to grams of Ki. Okay, let's fill in our numbers. The middle ratio is mole to mole. We use the coefficients. For Ki and K, they have a coefficient of 2. So I'm going to put a 2 on both of those. 2, 2. My other conversions are moles to grams. I use 1 mole equals the molar mass grams. 1 mole equals the molar mass grams. So I put my 1 in front of the moles. Let's start with the potassium down here. The molar mass is just straight off the periodic table. Potassium is 39.10. And Ki up here, let's add that up. It's going to be potassium 39.10 plus iodine is 126.90. So that's going to be 166. All right, so let's calculate what we have here. It's going to be 15.0 times 2 times 166 divided by 39.10 and divided by 2. We've got 63.7. That's grams of Ki. All right, let's do the other one. We're going to start now with our 15 grams of iodine. So 15.0 grams of I2. We're going to set it up so similar. It's just that we're starting with iodine instead of potassium, but we're going to the same place. We're still going to grams of Ki. So I'm going to bring down grams of I2 and go to moles of I2. I'm going to bring down moles of I2, and I'm going to go to moles of Ki. I'm going to bring down moles of Ki, and I'm going to go to grams of Ki. This last ratio is going to be the same, 1 to 166. The ratio before it is moles to moles right here. So it's going to be the coefficients. Ki has a coefficient of 2 and I2 has a coefficient of 1. And finally, back here where this arrow is, I've got moles to grams. So that's 1 mole equals the molar mass grams. I2 is 126.9 times 2, 253.8. That's the molar mass of I2. All right, so let's calculate. I've got 15.0 times 2 times 166 divided by 253.8, and I get 19.6 grams of Ki. All right, which of these answers is the lie? It's wrong. It is the bigger one. We want the smaller answer. So this whole one that gave us the bigger answer is a lie. So the real amount of product produced is the smaller answer. So let's write a little bit at the bottom here. 19.6 grams of Ki is actually going to be produced. And what was our limiting reactant? Well, whatever our answer was, whatever chemical we started with was our limiting reactant. I'm going to draw that again. Watch this if you missed it. Whatever our smaller answer was, the one that we started with was our limiting reactant. I like to label it LR sometimes. So I can say that I2 is the limiting reactant. So there is my answer. All right, y'all, let's talk about one more topic. Let's talk about how do you find the amount of excess left over. So let's revisit the dishes and silverware. How many napkins would be left over after you make as many place settings as you can? Well, napkins, I have 10 available. So I'm going to write 10 napkins available. Okay, now let's think about how many napkins we're going to use. Well, if we have 3 plates, that's my limiting reactant, right? I would use 3 napkins. Okay, so if I have, here's my little calculation down here. I've got 10 napkins available minus 3 napkins used equals 7 napkins remaining. So what did this boil down to? If we know how much of a chemical we have and we know how much we used, then we can figure out how much remains by subtraction. All right, so here we go. If you calculate the amount of excess reactant needed or used to completely react with the limiting reactant, you can subtract the reacted amount from the given amount to find the amount of excess. So again, I like to kind of summarize this by you take the amount that you have minus the amount that you used, and that's going to tell you the amount remaining. Okay. So we have one more problem. We have 15 grams of potassium with 15 grams of iodine. Oh, hey, that's the same thing that just happened. Okay, we're going to determine the excess reactant and how much is left over. Let's scroll back. I'm going to scroll. You just look back. Back in this 15 grams of potassium with 15 grams of iodine, what was our limiting reactant? Well, our limiting reactant was iodine. So here's our chemical reaction. What that tells me is that iodine was used up. That's called the limiting reactant. So what does that tell me about the other chemical, potassium? That means that there was extra. Okay, there were some leftovers because the iodine was used up, the reaction stopped, and there's some potassium left over. So if the limiting reactant was iodine, then the excess reactant is potassium. So the first part of the question is, what was the excess reactant? So we can say that the excess reactant was potassium because the iodine was the limiting reactant, so potassium was the excess reactant. Okay, so next up, how do we figure out how much of the excess reactant was actually used? Okay, because to know how much is left over, I'm going to kind of think about my final calculation here. I need to know how many grams of potassium that I have. Well, that's 15. Minus how many grams of potassium got used, and that's going to tell me how many grams remain at the end. So how do I figure out how much potassium is actually used? Well, once you know it, the limiting reactant determines everything. So I'm going to do a calculation from iodine back to potassium, and that's going to tell me if all the iodine was used, how much potassium gets used as well. So I'm going to set up my conversion here. Again, one more time. Once you know it, everything starts with the limiting reactant. So my limiting reactant was iodine. I have 15 grams. I'm going to bring down grams of iodine and go to moles of iodine. I'm going to bring down moles of iodine. And this time, y'all, what are we trying to find? Everything we're trying to find is about potassium. So we're trying to go to moles of potassium and find out how much was used, right? How much was used. And then moles of potassium to grams of potassium. All right, let's plug in some numbers. Mole to mole, coefficients. Potassium is going to be a 2. I2, iodine, is going to be a 1. I realized I forgot to write I2 there. So that's 2 potassiums, 1 iodine. Moles to grams is 1 mole. And the molar mass is what we use for grams. Starting over here with potassium, that's 39.10 from the periodic table. Iodine, I'm going to scroll up. I know I have this written here. The grams of iodine is right here, highlighting it in red. 253 grams of iodine. .8. All right, so we're ready to calculate this stoichiometry calculation. So I'm going to do 15 times 2 times 39.10 divided by 253.8. I get 4.62. That's grams of potassium, and that's grams of potassium used. Stoichiometry tells me how much I'm going to use. So I'm going to subtract 4.62. So down here, we're ready for my final calculation. I have 15. Here's what I'm doing. I have 15 grams. I used 4.62, so I would subtract minus 4.62. And so my answer is 10.38. So I'm going to zoom in down here. 10.38 grams remain. I'm going to highlight here in yellow my answer. 10.3 grams of potassium remains. All right. Last thing we have here is just a recap of what we've learned today. Feel free to pause it if you want to write all this down, but I'm just going to walk you through it. Number one, you can recognize the limiting reactant problem. So how do you know it is? Recognize the limiting reactant problem because there is more than one given reactant amount. We're mostly going to have problems where they give you 2 reactant amounts. Your first step is to convert all of those reactants to the same product. Pick any product you choose. If you have more than one, you can choose whichever one you want. The lowest answer is the correct answer. Remember, the higher answer we exit out. It is not true. The reactant that gave you the lowest answer, so the reactant that gave you the lowest answer is the limiting reactant, and the other reactant is excess. To find the amount of excess, you subtract the amount used from the amount given. All right. So that is it. This last little bit here says if you have to find more than one product, be sure to start with the limiting reactant. So that's really a key thing. Once you know what the limiting reactant is, you always start with the limiting reactant and every other answer is based off of that. Thank you so much for watching. I hope this was a helpful introduction to limiting reactants. If you have any questions, please feel free to come and ask us, and we are happy to help. Have a good day.